This is AP Podcast 3.3. This is the beginning of our new chapter. We're going to talk about energy, work, calorimetry, and specific heat. All right, so things you need to know. We're going to start with just kind of general definitions and things that you need to know about some of these words. Energy is the ability to do work. That's its definition. Energy is always conserved, so you can't destroy or create energy. Energy is made of heat and work, and it is a state function. And a state function just means it doesn't matter the path you take to get from point A to B. Whatever path you take, you still end up with the same amount of energy being put in or being given off. So it's a state function. It doesn't matter on the pathway that you take. And here's a picture over here of that example. You can see that in path 1, it's just a one-step reaction. You have the sodium ion and the chloride ion forming the sodium chloride solid. And then if you look on path 2, it has a bunch of smaller steps. But either way, the change in energy, and this delta H right here really is enthalpy, but we'll get to that in a second, is negative 411 kilojoules per mole. So it doesn't matter which pathway you take, you still end up with the same change in energy. All right, so work. Work and heat we just talked about. Being energy is a combination of work and heat. So work is a force acting over a distance, and there's the definition. Work is force times distance. And heat is the energy transferred between objects because of the temperature difference. And you need to know that heat always flows from hot to cold. So from the hotter object to the cooler object. All right, the universe. When we talk about the universe, we need to understand that the universe is made up of two parts. We have the system and we have the surroundings. And the system is the part that we're focusing on. It's where the reaction's taking place. Then the surroundings is everything else. You can have exothermic reactions or endothermic reactions. Exothermic is where we have energy exiting the system. It's leaving, it's being released. Endothermic is when energy is coming in, it's being absorbed from the surroundings. And those are two really important definitions that you need to make sure that you know. Here's just a diagram to illustrate exothermic versus endothermic. You can see in this picture, the potential energy is starting higher for the reactants than it is for the products. So that change in energy is being released out into the surroundings as heat. You would see it as an increase in temperature if you were monitoring the temperature while this reaction took place. And you would see the temperature go up. So that's your exothermic reaction. We'll see increase in temperature. In this one, we have the reactants that are starting at a lower energy from the products. So we're having to put energy in. That means heat is being absorbed from the surroundings. So you're going to see the temperature drop because it's pulling in that heat and it's being used for this reaction. Okay, direction is everything when we talk about energy. So every energy measurement has three parts. We have the unit. The unit is the first part of an energy measurement, and it's usually in joules or calories. And then we have the quantity, a number to tell us how many. And then we have the sign. So the unit that it is, the quantity, so we know the amount, and the sign. And the sign is either a negative or a positive. If it's a negative, it means it's exothermic. If it's a positive, it means it's endothermic. And that's just what this is illustrating down here. If energy is leaving the system to the surroundings, your change in energy is going to be less than 0. It's going to be negative. If your system is absorbing energy from the surroundings, your change in energy is going to be positive. You'll have an endothermic, exothermic. All right, heat and work. Heat that is given off is negative in value, so you're going to see a negative number associated with heat that is given off. Heat that's absorbed is positive, and this is kind of restating what we just talked about on that last slide. All right, work done by the system on the surroundings is negative. And work done on the system by the surroundings is positive. And we'll give some examples of what work could be. Okay, first law of thermodynamics. Thermodynamics is what we do to study the energy and the changes it undergoes within chemical reactions. So that is the definition of what thermodynamics is. Chapter 6 is the start of thermodynamics. We're going to get more into it in chapter 16. The energy of the universe is constant. The law of conservation of energy, we talked about that when we briefly talked about energy right at the beginning, how we said it's conserved. Here are some equations. Q is what we use to represent heat. That's the variable that we use. W is for work. And the change in energy is equal to the heat plus the work. And that goes right along with what we said at the very beginning, that energy is made of heat and work. When we're doing these, we always want to make sure that we take the system's point of view to decide the signs on heat and work. So we're looking from the system's point of view, we're looking at where is this reaction taking place and what's happening. So our example here of internal energy, calculate delta E, which is the change in energy, for a system undergoing an endothermic process in which 15.6 kilojoules of heat flows and when 1.4 kilojoules of work is done on the system. So we know our equation, delta E equals Q plus W. And Q is the heat. So if we look here, it says 15.6 kilojoules of heat flows. And we know that this is an endothermic process. So that tells me that heat is going to be positive. So I'm going to have 15.6 kilojoules plus, and then it says because it's done on the system, this work is done on the system, that's also going to be positive. I do need to double check that my units are the same, and they are. They're kilojoules for both. So all I'm going to have to do on this is just add the two up. So it's going to be 15.6 plus 1.4, and I'm going to get 17. So the change in energy for the system is 17 kilojoules. All right, so let's talk a little bit more about work. Work is the force acting over a distance. We already gave that definition. Here is the formula for it. Work equals force times the change in distance. Pressure is equal to force over area, and distance is equal to volume over area. So what we can do with this is if we combine all of it, we end up with this new formula that work is equal to P delta V, and that's pressure and volume. So we can use these, substitute in, and we get this formula right here. Work can be calculated by multiplying pressure by the change in volume at a constant pressure. So when we're holding the pressure constant and we have a change in volume, we can calculate the work that's done. Units of work are liters times atmosphere, or liter times atmosphere. And I'm going to see if it's on the next slide. It is right here. That liter atmosphere can get you to joules. So 1 liter atmosphere is the same as 101.3 joules, and that's a really important conversion factor that we're going to use in just a second. So if the volume of a gas is increasing, the system has done work on the surroundings. If you think of, I guess if you think of maybe a balloon or even something with a piston, if it expands in size, it's doing work on the surroundings because it's pushing out on the surroundings. So in this, work is done on the surroundings. Work is going to be negative, so we would use this equation instead. We'd have to throw in that little negative sign because we know work is supposed to be negative. Expanding work is negative, that's what we just said. Contracting surroundings are doing work on the system. So if we have a gas where it's getting smaller, that means the surroundings are doing work on the system and work is going to be positive. And that's when we would use this without that extra negative sign. So if the volume of the gas is going up, we are going to have negative work. If the volume of the gas is going down, we're going to have positive work. And then again, here's that conversion factor for us to use. All right, so our example 2 question here. What amount of work is done when 15 liters of gas is expanded to 25 liters at 2.4 atmospheres? Well, the first thing we need to think about is work. Is it going to be positive or negative? And they're telling us that the gas is expanding. So that tells me that work needs to be negative. So I'm going to use that equation that work is equal to negative pressure times the change in volume. So negative, and the pressure they gave me is 2.4 atmospheres. And then my change in volume is going to be the final minus the initial. So 25 minus 15 liters. And if I do that, I end up with negative 24 liter atmospheres. Remember, those are the units. But if we wanted to convert to joules, we could do that dimensional analysis with that conversion factor that we just said. That 1 liter atmosphere is the same as 101.3 joules. And you could do that math, and then the answer would come out in joules. All right, our next problem says, if 2.36 joules of heat are absorbed by the gas in example problem 2, what is the change in energy? And if we'll remember back, the answer to problem number 2 that we just solved was negative 24 liter atmospheres. So we're trying to figure out what is the change in energy. So we're going to use this guy. So we're going back to this equation that we just talked about. We calculated the work. So delta E is going to be equal to the heat that they gave us in this problem needs to be in joules first. So if we did that conversion factor from the previous problem, heat's got to be in joules. So negative 24, we'll just set this up and do it. And then we'd put the 1 liter atmosphere on the bottom and the 101.3 joules on top. And when we do that, we end up with negative 2,431.2 joules. I need joules because Q is always in joules. So, Q is in joules here. So I need my units to match up so I can add them. That's why I had to convert works units into joules. That way we could add them up in this formula. So the Q that they gave me here is 2.36 joules of heat are absorbed. So that means that I have a positive heat. I'm going to leave that as a positive number. Plus, I need to do the work. Well, the work was negative, so it's plus a minus 2,431.2 joules. And when I do that and I add them up, I get negative 2.43 times 10 to the third joules. So let's recap. We were doing change in energy, so we used this formula. We got the work from the previous problem that we just did. We had to change works units to match our heat units. That's why we used this little conversion down here that we talked about. The 101.3 joules is the same as 1 liter atmosphere. When we did that, we ended up with joules, so we were able to plug it in. And since both of these are joules, we can just add up our values and get our answer. Okay, enthalpy is another variable that we talk about a lot with thermodynamics. Enthalpy really means the energy that flows during a reaction. Enthalpy is abbreviated with an H. I don't know why, that's just how it is. Here's kind of the generalized version of the formula you'll use that involves enthalpy, but the one that you see the most and you're going to use the most is this one right here. When we hold the pressure constant, this is the one that we're going to use. The change in enthalpy, or the change in heat of the system, is the products minus the reactants. Just like if we were doing the change in volume, it would be products minus reactants. Final volume minus initial volume. And then if your enthalpy is negative, it means that energy is flowing out. It's an exothermic reaction. If you end up with a delta H that is positive, then you have energy that's flowing in. So doing these problems, we have, when 1 mole of methane is burned at a constant pressure, 890 kilojoules of energy is released as heat. Calculate delta H for a process in which a 5.8 gram sample of methane is burned at constant pressure. So what they want us to do is figure out, if I know that for every 1 mole of methane, 890 kilojoules of energy is released, you kind of do a ratio. Then what would be released for only 5.8 grams of methane? So the first thing I want to do is figure out how many moles is that, because like a lot of things that we do in chemistry, the enthalpy is directly related to the moles in the balanced equation, or the moles that they give you in the problem. So I have 5.8 grams of methane, and methane is CH4. So if I add that up, it's 16 grams is 1 mole. And when I do that, I get 0.36 moles of methane. So I know that for every 1 mole of methane, I get 890 kilojoules of energy released. I can use that as a conversion factor, or you could set up a ratio. If I have 0.36 moles, I know that for every 1 mole that there is, we would lose 890 kilojoules of heat. So when I do that, I multiply them together, and I end up with a negative 320 kilojoules. So if 1 mole of methane releases 890 kilojoules of energy, 0.36 moles of methane is only going to release negative 320 kilojoules. So you can use these as conversion factors, and we can just do conversions like we did down here, stoichiometry problems with these. So let's talk about finding delta H using calorimetry. And we've done calorimetry before. We did it last year. You use a coffee cup calorimeter, and you have your 2 styrofoam cups that you pack in next to each other. You have your thermometer, and then you have the solution in here, which you're stirring and measuring the change in temperature as it goes. So this is a way that we can measure heat. It's at a constant pressure because it's the same as the pressure in the room. It's the same atmospheric pressure. It's not sealed off tight. The equation that we use is Q equals mc delta T, Q being the energy or the heat, M is mass, C is the specific heat. And remember, that's the number that you look up. It's unique for each substance that we use. And the T in this case needs to be in degrees Celsius. So we just finished with gas laws where everything needed to be in Kelvin. Now you need to make sure that all your temperatures are in degrees Celsius, just to make things a little more confusing. All right, specific heat and molar capacity, that was that C. The specific heat capacity is the energy required to raise the temp of 1 gram of a substance by 1 degree Celsius. You guys know this, you used it last year. Your units are either joules per gram degree Celsius or joules per gram Kelvin. You don't very often see the Kelvin one, so it's really this one that you see the most often, where we have the degree Celsius for the temperature, and that's what we use for the specific heat capacity. And this is just giving you a visual of what happens, how they measure this. And we know for water it takes 4.18 joules per every gram of water to raise it 1 degree Celsius. Alright, so the lower the specific heat, the easier it is to heat it up or cool it down, so the faster you're going to get the temperature changes. The higher the specific heat, the lower and slower the temperature changes will be, because it's going to be harder to heat up those substances with really high specific heats. Molar heat capacity is just another version of the specific heat where we talked about joules per gram degree Celsius, except this is in joules per mole degree Celsius. So your molar heat just uses moles instead of grams. Okay, here's an example using specific heat. The specific heat of graphite is 0.71 joules per gram degree Celsius. Calculate the energy needed to raise the temperature of 75 kilograms of graphite from 294 Kelvin to 348 Kelvin. So we can use the Q equals mc delta T. And we're going to be calculating Q here. They give us the mass, and it needs to be in grams. So that's going to be 75,000 grams. That is a big piece of carbon. Okay, specific heat of carbon, specifically graphite, is 0.71 joules per gram degree Celsius. And the phases or the states that these are in, it does affect the specific heat. So it's important that we know that it's graphite, not diamond. We need to know the difference because that will change what those specific heats are. Just that's the same reason that water, ice, and steam all have different specific heats, because they have a different structure. So I have my mass, my specific heat, and then I need my change in temperature. So I'm going to take the final, which is 348, and I'm going to subtract, I don't know if it's 348. I think I might have made a typo. I'm thinking yours says 358. So 358 minus 294 Kelvin. All I do is plug all that in, and I'm going to find out that Q is 3.4 times 10 to the 6th joules. That'll be joules. That is such a big number, I'm going to go ahead and convert that to kilojoules. So I'm going to divide by 1,000. So that's going to give me 3.4 times 10 to the 3rd kilojoules. So it takes that much energy to raise 75,000 grams of graphite from 294 Kelvin to 358 Kelvin. Okay, example problem number 6 is about specific heat again. This time though, we are using the calorimeter and we're trying to determine the specific heat of copper in this case. This is a really common procedure that people will use if we have an unknown metal. We can do this procedure where we heat up the metal to a certain temperature, then we drop it into the calorimeter, measure the change in temperature, and what we can find is the specific heat of whatever metal we're looking at. Then we can look up specific heats on a table and we can probably identify what that metal was. So this is a way you can identify unknown substances, is by finding their specific heats through calorimetry. But in this problem they're telling us it's copper, but they just want us to calculate the specific heat of copper. So when we're doing these, we need to remember that the heat lost is equal to the heat gained. And either the metal or the water is going to be losing energy and the opposite one has to be picking it up. So when you're looking for heat lost, we want to think of the substance that is going down in temperature, and that would be the copper. The copper is starting at 95.4 degrees Celsius, and it's ending up at 19.6. Nope. It's ending up at 21.8 degrees Celsius. The water is starting at 19.6 degrees Celsius and it is ending up at 21.8. So the water is gaining the energy from the copper. It's flowing from the copper to the water. And what we're going to do then, since heat lost equals heat gained, we know that heat is equal to mc delta T. So we're going to take and set mc delta T equal to mc delta T. And we can do that because the heat that's lost by something has to be the heat that's picked up by something else. So these are going to be equal in amount. So the mc delta T's must then also be equal for the two substances. And we'll put all of copper's information on one side and then all of the water's information on the other. And it just becomes kind of a plug and chug problem. You just put things in where they belong and you solve for what you don't know. The mass of our copper is 46.2 grams. We do not know the specific heat of our copper, but we do know that it started at 95.4 and ended up at 21.8. And then for our water had 75 grams. We know the specific heat of water is 4.18. And we'll be a little more specific and go 4.184. And then I don't want to end up with a negative specific heat, so I'm going to take the 21.8 minus 19.6. When you're doing these, you need to make sure your delta T's are always positive. So always positive. So I just do all of this and I end up with the specific heat for copper. And once you plug all that in, you're going to get 0.203, and the units are joules per gram degrees Celsius. And this is a reasonable answer. Your metals should have pretty low specific heats, and it does. So that's how you do those. Okay, so you need to make sure that you kind of understand whether energy, work, and heat are positive or negative based on what's happening in the situation. Make sure that you can calculate heat using mc delta T. And then make sure that you can also set up the formula for mc delta T equals mc delta T when we're talking about coffee cup calorimeters.